All right, so the last set of two examples we're going to look at ask us to find the rational function whose graph is provided. Okay, so this is a little bit different than the previous examples. The previous examples, we were given a rational function and asked to sketch the graph. This time we are given the graph and asked to find the function that yields that graph. Okay, now when doing this, there is a specific order in which I want things done. Okay, so if you look in the box to the right of the graph, step number one asks us to find the x-intercepts. Step two asks us to find the vertical asymptotes. Step three is to determine the horizontal asymptote. And then step four is to check the y-intercept. Okay, and this is the process that we want to use to come up with the functions that give us this graph. Okay, so when we look at number one, we see that the function for number one has an x-intercept at x is equal to 0. So that means that x minus 0 or x has to be a factor in the numerator. And because the graph touches the x-axis at that point, that tells us that the multiplicity of that 0 or the exponent for that factor has to be an even number. Okay, so we're going to write that as having an exponent of 2 for the time being. Okay, next we want to determine the vertical asymptotes. So we have vertical asymptotes at x is equal to -2, which means we have to have a factor of x plus 2 in our denominator. And it also has a vertical asymptote at x is equal to 2, which means that x minus that number, x minus 2, has to be a factor in our denominator as well. Okay, now when we look at the behavior of our graph at those vertical asymptotes, we see that the graph goes in opposite directions as we approach the vertical asymptote on each side. So as we approach the vertical asymptote at x is equal to -2 from the left-hand side, that goes to infinity. As we approach the vertical asymptote at x is equal to -2 from the right-hand side, that graph goes to -infinity. Okay, so because the graph goes in opposite directions there, that tells me that the multiplicity of that 0 in the denominator has to be odd. So x plus 2 has to have an odd exponent. We're going to keep that as 1 for the time being. And the same thing can be said at the vertical asymptote at x is equal to 2. As you approach that asymptote from each side, the graph goes in opposite directions. So one side goes to -infinity, one side goes to +infinity. So because the graph goes in opposite directions, that means the multiplicity for that 0 has to be odd as well. Okay, so we can leave the function in that form, or if you want to expand out the denominator, x plus 2 times x minus 2 multiplies out to x squared minus 4. Okay, now we're going to check the horizontal asymptote next. Okay, so the fact that the horizontal asymptote is the line y is equal to 1, that tells me two things. Number one, it tells me that the degree of the numerator and the degree of the denominator have to be the same. And it also tells me that the ratio of the leading coefficients has to be 1. And when we take 1x squared divided by 1x squared, when we take the ratio of the leading coefficients, 1 divided by 1 is 1. So that checks out for our horizontal asymptote. That's good. And then the last thing we have to check is the y-intercept. So if we plug 0 in the place of x and solve for y, that's going to give us 0 divided by -4, which is 0. And when we look at the graph of our function, that has a y-intercept at y is equal to 0. Okay, so that function checks out. This is our function here that is going to give us that graph. And like one other thing for us to check here is if we look at that graph of that function, we see that that function has y-axis symmetry. So if the function has y-axis symmetry, that means that the function needs to be even. And r of x, which is x squared over x squared minus 4, that is an even function. If we take r of negative x, that gives us back the original function that we started with. Okay, so that function there is going to be even. Okay, so I'm going to have you guys try number 2. You should be able to get to a certain point in this problem, and then I think you guys are going to get stuck, and then we're going to talk about how to work around the issue where you get stuck. Okay, so that right there is the graph of the rational function r of x, and we want to come up with the function that yields that graph. So go ahead and pause this, give that example a try. When you get stuck, which I expect just about all of you guys to get stuck, go ahead and unpause and we'll talk about how to work it through together. Okay, so when we look at number 2, we're going to work through our 4 steps in order. Okay, so we want to start by looking at the x-intercepts. So when I look at the x-intercepts, we have an x-intercept at 1, which means x minus 1 has to be a factor of the numerator. And because the graph crosses the x-axis at that point, that means the multiplicity for that 0 or the exponent for that factor has to be an odd number. Okay, so we're going to keep it as 1 for the time being. And it also has an x-intercept at x is equal to 3. So that means that x minus 3 also has to be a factor of the numerator, and the fact that the graph crosses the x-axis at that point means that the multiplicity again has to be odd. So that means that the exponent has to be an odd number. So again, we're going to keep that exponent as 1 for the time being. Okay, next we want to look at the vertical asymptotes. So we have a vertical asymptote at x is equal to -1, which is going to make x plus 1 a factor of my denominator. And when I look at the behavior of my graph at that vertical asymptote, the graph goes in the same direction as we approach that vertical asymptote from the left and from the right. So as we approach -1 from the left-hand side and from the right-hand side, both sides go to positive infinity, which means that the exponent for that factor has to be even. Okay, that 0 on bottom has to have an even multiplicity. And when we do the same thing at the next vertical asymptote, which is at x is equal to 2, okay, that has to make our factor in the denominator x minus 2. When we look at the behavior of our graph at that vertical asymptote, again, as we approach that vertical asymptote from each side, both sides go in the same direction. So as we approach the vertical asymptote from the left-hand side, it goes to -infinity. As we approach the vertical asymptote from the right-hand side, that also goes to -infinity. So since the graph goes in the same direction at the vertical asymptote, that means that that 0 has to have even multiplicity as well. Okay, so the third thing we want to check is the horizontal asymptote. So again, the fact that we have a horizontal asymptote at y is equal to 1 tells us 2 things. It tells us, number 1, that the degree of the numerator and the degree of the denominator have to be the same, which they're not here. The degree on top is going to be 2. The degree on bottom is going to be 4. And it also tells us that the ratio of the leading coefficients needs to be 1. So what I would have guessed that you guys would have tried next is to make like one of the exponents in the numerator like 3 and make the other one 1. But when we try checking the y-intercept, so when I plug 0 in the place of x and solve for y, we're going to get -1 cubed times -3 over 1 squared times -2 squared. And that's not going to give me a y-intercept of 1, okay, which this function has. It has a y-intercept of 1. Okay, so I would have guessed the next thing you probably would have tried is to make the exponent for the next factor 3 and to keep the first one 1. But when you try checking the y-intercept for that, that's not going to check out either. Okay, so we have a real problem then with this. And I can't add like other factors. So I can't add other linear factors to the numerator, because if I added like the factor x minus 2, then that would give us an x-intercept at x is equal to 2. Really, it's going to give us a whole here based on this function, but if we add linear factors in the numerator, that's going to increase the number of x-intercepts that our graph has, okay? So what we need to do for this is we need to find a way to increase the degree of the numerator by 2. We also need to keep the ratio of the leading coefficients 1. Okay, and we can't add a linear factor to the numerator. And we also have to make sure that our y-intercept checks out. Okay, so the way that we can do all of those things is if I multiply in the numerator by something of the form x squared plus c, that increases the degree of the numerator by 2. So that's going to make, now if I multiply out the entire numerator, that's going to make the degree of the numerator 4, which is what we want. It keeps the ratio of the leading coefficients 1, which is that's what we want for our horizontal asymptote. And if we find the correct c value, that's going to make the y-intercept what we want it to be as well. Okay, so what I want to do here is I want to find the value of c that gives me the proper y-intercept. Okay, so when we take r of 0, the y-intercept of that function is going to be 1. Okay, so r of 0 is going to be equal to 1. And then we're going to plug 0 in the place of x. And then we're going to solve this equation here for c to give us the c value that's going to give us the proper y-intercept. Okay, so we're going to get 1 equal to, in the numerator, -1 times -3 is going to be 3 times c. And then in the denominator, -2 squared is 4 times 1 squared. 4 times 1 is going to be 4. And then when I isolate c, I can multiply both sides by 4/3, and we get c equal to 4/3, which is going to make my function r of x equal to x minus 1 times x minus 3 times x squared plus 4/3. Okay, so the fact that we are taking x squared and adding 4/3 to it, that's not going to be factorable, okay, which means the numerator does not have any more factors, which means that graph is not going to have any more x-intercepts, okay? And then we are dividing that by x plus 1 squared times x minus 2 squared. Okay, now if I were to ask you something like this on a test, this example here is probably above what I would ask you on a test. And the first example is probably too easy. So you're going to get something kind of like in the middle between these two examples as a test question. Okay, so that right there wraps up the lesson on rational functions. We have one more lesson to go through, which deals with polynomial and rational inequalities, and that's going to wrap up chapter 2. Okay, so just a reminder for you guys, you have your quiz on the first half of chapter 2 on Monday, and then you guys are going to take your chapter 2 test not this coming week, but the following week. Okay, all right, hope you guys have a great day. We'll see you soon. Bye.